In this video, we will try to model situations which involve periodic behavior. And of course, we will use sinusoidal functions. So let's take a look at our first example. The height in meters above the ground of a rider on a Ferris wheel after t seconds can be modeled by this sinusoidal function. So what I'm going to do is generate a graph before I answer the questions. Because I think that will help us out a little. Because what we're going to do is see how the equation changes. Now we don't have to generate a graph, but I think for a lot of the examples that we're going to do in this sheet, it would be very beneficial to have the graph of the sinusoidal function. It's going to help us better understand the scenario. Alright, so luckily I know how to graph a sinusoidal function. So we have h, we have t. Alright, so the minimum value, so c is 22 and the amplitude is 20. So c minus the amplitude is 2 in this case, so that's our minimum value. The c value is actually 22, and then the max value is c plus the amplitude. So 22 plus 20 will give us 42. And for the horizontal axis, it would be really helpful to know the period. So the period is 360 over k, which in this case is 30. So the period is 12. So what we have is a very fast Ferris wheel. It's going to start at the bottom of the Ferris wheel because we're working with a cosine that's been reflected across the x-axis. So the first point I plot is a minimum, and then you don't really need these values, but I'll give it to you anyways, because this is a quarter period, right, to plot these key points. So quarter period would be 3, is 12 divided by 4 is 3. All right, there we go, 3, 6, 9, 12. All right, beautiful. So like I said, you don't really need to have the graph, but I feel like it will help us out. And using these values, the 2 and the 22 and the 42, I'm also going to draw, I'll try my best to draw. Oh, that's horrible. That is, I have to try again. I have to draw way closer to the ground. Okay, because the minimum height of the rider is 2. Okay, and the radius of the wheel is 20. And if you look, that's how you get a maximum height of 42, because it's 2 plus the diameter, so 2 plus 40 is 42. Okay, I think we have enough information to answer the questions. We visualize the situation. Hopefully this equation makes sense when you're pretending to be a rider on the Ferris wheel. And like I said, the graph is very beneficial. It gives you another way to visualize what's happening. All right, so if the Ferris wheel was twice as fast as before, how would the equation change? Well, if it's twice as fast before, guess what? Your period is no longer 12, your period is 6. Wow, it's going to be extremely fast. So you would say k, the magnitude k is 360 over 6, which is 60. Therefore, the equation, assuming of course everything else is the same, would be minus 20 cos of 60t plus 22. Okay. I put the degree symbol here. Some textbooks do, some textbooks don't. Depends on textbook. So Nelson doesn't and McGraw-Hill doesn't. But I would prefer if the degree was there, if the degree symbol was there, because in grade 12 we don't put the degree sign. But because in grade 12 you don't work with degrees, in grade 11 you do work with degrees, so we need an indicator. So it's best to put there, so we know what unit the angle should be in. All right, for B, how would the equation change if the center of the wheel is raised by 5 centimeters? Well, let's see. Right now, which number here represents the height of the center of the wheel. And hopefully you can agree, well, let's look at our diagram right there. This is the height of the center of the wheel, 22. The C value represents the height of the center of the wheel. So since C is now 27, it's 22 plus 5, therefore the equation will now be, and again, assuming everything else is staying the same, 27. Okay? And lastly, how would the equation change if the radius of the wheel decreased by 7 meters? Well, so now the amplitude will no longer be 20, it'll be 20 minus 7, which is 13. So we're going to say the new equation is, whoops, it'll be minus 13 instead of minus 20. Awesome. Okay. So by changing scenario, obviously you'll change the sinusoidal function, but you have to change it accordingly. So this question was nice because it helps you understand the effect of the parameter with respect to the situation. All right, so let's see, number 2. The height h in meters of the tide on a given day t hours after midnight can be modeled using this sinusoidal function. Beautiful. What's the maximum depth and what's the minimum depth? All right, so the max value is equal to c plus the amplitude, which in this case is 7 plus 5 is 12. And the minimum is c minus the amplitude. So in this case, that's 2, 7 minus 5. Therefore, max depth is 12 meters, and minimum depth is 2 meters. What is the depth of the water at 9 a.m.? Well, h of 9, because it's 9 hours after midnight if it's 9 a.m. And then just punch in a calculator. Is that a special angle? 9 minus 5 is 4. Ooh, it is. Sine 120. So you know what? I'm going to keep it as exact answer because I can. So this would be 120 as second quadrant. So reference angle 60 degrees. We're looking at root 3 over 2. You can simplify that a little. Beautiful. Special angles. Best friend. Therefore, the depth at 9 a.m. is 5 root 3 plus 14 over 2 meters. Okay, so 2C, this question is something that a lot of students struggle with. So hopefully my explanation is sufficient here. So find all the times during a 24-hour period when the depth is 3 meters. Okay, so before we even begin to answer this question, what we should ask ourselves is, how many answers should you get? How many times do you expect the depth of the water to be 3 meters during a 24-hour period? I can't stress how important that is, because many students, when they do the math, they get one answer and then they walk away. But if you truly understand the sinusoidal function, the period of this function, by the way, is 12, because 360 over 30 is 12. The period is 12 hours, which means in a 24-hour period, you should expect there to be 4 moments where the depth of the water is 3 meters. Because 24 hours, you're going to draw 2 cycles, right? You should get 2 answers. So we should get 4 answers, but the question is, how are we going to get 4 answers? So with that expectation in mind, let's progress. So let h of t equals 3. So we have sine of 30, and what do you have? T minus 5 plus 7. Okay, so we're going to subtract both sides by 7. I'm going to take it very slow here. and divide both sides by 5. Okay, now here's a critical moment. You take the inverse sine of negative 4 or 5. But be careful. How many answers should you get from this? You should get an infinite number of answers. Now you might be tempted to say 2 first. Okay, so we're going to say 2. 2 because quadrant 3 and quadrant 4, that's where sine is negative. So let's write that down. Quadrant 3, quadrant 4, casserole. Okay, hopefully you didn't forget. So we're going to inverse sine. So let's get the quadrant 3 answer. So the quadrant 3 answer says that 30 times t minus 5, okay, the angle is equal to about 233.13. Okay, let's give some more. Why not? Okay, so wait a minute. Okay, you know, let's also solve for the fourth quadrant answer. So 30 times t minus 5 is approximately equal to, so the fourth quadrant answer, that's 306.8698. You know, let's not do too many because I need the space actually. So I won't change anything. Okay, all right. So I said there are infinite answers, but right now all I see is 2 answers. How come there are infinite answers? So yes, if I type in sine 233 degrees, approximately I'll get a ratio of negative 0.8. But we have to consider, and this is a term we learned in the previous unit, coterminal angles. 233 degrees, approximately that angle will give me a ratio of negative 0.8. But there are infinite angles that can do that. Anything coterminal to 233 will give me this ratio. So anything coterminal to 233, bam. Anything coterminal to about, let's say 307 degrees, okay? And then I'm out of room here, but I'm just gonna write n is an integer, okay? It's the same logic we had it in the very first lesson when we talked about periodic function, okay? N is an integer. All right, let's solve for t here. And then it will not be 360n anymore. It'll be magical. I don't want to spoil it, but this will change to a number that is very friendly. $12. Beautiful. 12. Why is 12 so beautiful? Because 12 is the period. It makes sense. If we have a solution, you can find the subsequent solutions by adding by the period. It's a periodic function. Okay. So we're looking at, I guess you can say during the 24-hour period. So since you're basically looking at a 24-hour time frame, then our answers are equal to 0.77, right? You subtract by 12, right? You get one answer. If you subtract by 12, this will be 3.23, 12.77, and 15.23. So we're going to convert these to times, okay? So 0.77, so that's 46 minutes after midnight, okay? 0.77 hour after midnight, that means that's, let's see, that's 12:46 a.m. And then, of course, I'm gonna cheat. I'm gonna write this answer because if this is 12:46 a.m., this would be 12:46 p.m. which makes sense because the period is 12 hours. What about this one? 3.23. So really, I just want to know 0.23 of an hour. That's 13 minutes. 13.8, but that means it's still 13 minutes past the hour. So 3:13 a.m. and 3:13 p.m. are the times when the depth is 3 meters. Okay, so this is the question which really bothers a lot of students. You first have to remind yourself about the casserole. Okay, and then you have to remind yourself about coterminal angles. So that's how you get all the solutions, and then based on the restriction of the situation, then you reject whatever solutions that don't fit the criteria. So for example, if they change the question, let's say find all the times during, I don't know, like the first 12 hours after midnight. Okay, then that changes the situation, that changes the domain. So you would have to study your solutions and go from there. But remember, okay, n is an integer, and that makes sense if you want to study the coterminal angles. All right. Okay, we'll do another example. Okay, a Ferris wheel has a radius and of 30 meters and rotates 3 times every 72 seconds. At the bottom of the ride, it's 2 meters above the ground. You start at the bottom of the Ferris wheel. So you know what? Let's just draw the graph. Okay, do we need the graph? No, but I will give it to you anyways. Because it's so quick, why not? So we're looking at a radius of 30 and the minimum height is 2. And then you start at the bottom. Oh, that is not pretty. I'm so sorry, but we're gonna live with that. Oh, hopefully you did a better job. So we're looking at rotates 3 times every 72 seconds. So what's 1 time? So the period is 72 over 3, which is 24, of course. Beautiful. If you start up on a Ferris wheel and stay for 2 revolutions, you're basically drawing 2 cycles. When are you 20 meters above the ground? So if you see, let's say 20 is right here, how many answers should you get? You should get 1, 2, 3, 4. You should get 4 answers. Okay? You should most definitely get 4 answers. So let's hunt for these 4 answers. We got to build the equation. So h of t is equal to the negative 30 cosine. Now the k is 60 over 24. 360 over 24 is 15. And what's the c value? 32. That's the height of the center of the wheel. Okay, let h of t equal 20 and let's go for it. Oops, this is 15 here. All right, subtract both sides by 32 and then divide both sides by negative 30. So that's negative 12 over 30, which I can reduce, but you know what? I'll leave it for now. It's not my final answer anyways. That's okay. So now I'm going to take the inverse cosine of 12 over 30. You know, sorry, before I do it. So my expectation is quadrant 1 and quadrant 4. Quadrant 1, quadrant 4. So inverse cosine of 12 over 30. Oops. So 15t is equal to 66.4218 plus 360n. The quadrant 1 answer and any angle coterminal to that quadrant 1 answer. 15t is equal to, and the quadrant 4 answer, right? Let's not forget about that. 293.578. Let's do 2 plus any angle coterminal of that. And let's say, of course, n is an integer. Time to solve for t, which is very easy. Divide both sides by 15. And that 360 becomes one of our friends. What does it become? You guessed it. 24, the period, which makes perfect sense. The rider is back at the same spot on the Ferris wheel after every 24 seconds. Beautiful. The logic makes perfect sense. Now be careful. Based on the graph, I'm only accepting between 0 and 48, right? So, 20 meters above the ground, after 4.43 seconds, 19.57 seconds, 24, so it's 28.43 seconds, and plus another 19.57 plus 24, perfect. About 43.57 seconds. You see these answers? These answers are between 0 and 48, which is exactly what makes perfect sense, because the rider is on this wheel for 2 revolutions. No more, no less. Okay, so I got my 4 answers. I'm very happy. Okay, so let's move on to the last example. The diameter of a car's tire is 40 centimeters. While the car is being driven, the tire picks up a nail. How high above the ground is the nail after the car travels 20 meters? In this case, I think it'll be very beneficial to draw the graph. Now, before I draw the graph, let's try to visualize the situation. So you have a tire here. Okay, unfortunately it picks up a nail. Okay, picks up a nail, and as you drive forward, the nail is going around and around and around. Okay, so I guess you can say the maximum height of the nail will be right here, which is also the diameter of the car's tire. So let's try to draw the graph here. Oops, I made a boo-boo. So t is not your independent variable. Your independent variable is the distance traveled by the tire. Okay? That will dictate the height of the nail. So the height begins at 0, and like we said earlier, it reaches a max height of 40, so which means the C value is 20. But what we don't know about this situation right now is the period. What is a period? Well, to answer that question, how far did the tire travel? How far did you have to move forward in order for this nail to make one full turn around the tire, sorry. And hopefully you realize that the answer is the circumference. The period is the circumference. If you travel by the circumference forward, if the tire travels by the circumference forward, then guess what? The nail will be back at the ground level. So the period is 2 pi r, or pi d, so it's 40 pi, which means your k value is equal to 9 over pi. I know that seems very strange, but that's your K value. We know amplitude, right? Amplitude is 20, C is equal to 20, D is equal to 0. Or I can choose, D could be different, but I'm going to model it without a horizontal translation. So therefore, H of D equals negative 20 cos of 9 over pi D plus 20. So H of, I made a boo-boo. So D is in centimeters here. D is in centimeters because the diameter is in centimeters. So I need to take 20 and multiply by 100 because there's 100 centimeters in a meter. So I want to find H of 2000. All right, let's see what the calculator says. We're looking at about 2.75. All right. So for these situations which demonstrate periodic behavior, you want to model it using a sinusoidal function. And each parameter, A, K, D, and C, represents something relative to the situation. So try to interpret that. Drawing a picture will help, graphing it will help. And I think the idea that bothers the students the most is really the infinite solutions, introducing what we learned from the previous unit about coterminal angles, but really try to understand that. If you look at your graph here, it makes sense. If this individual, if the rider lived on the Ferris wheel, there would be an infinite number of answers. Okay, you only have 4 answers for example 3 because you restricted the domain. But imagine if someone did live on the Ferris wheel, as strange as that sounds, then you have to show that there are infinite solutions. And I know that the notation looks weird, but that's what you need to do in order to show the infinite solutions. Anyways, hopefully you can appreciate how we related coterminal angles with the solutions here, and you have a better understanding of modeling periodic behavior.